Okay, so we'll come to this further some problems. So by varieties of problem in circuit, if you see that, then your understanding will be much more clear. So for this circuit, if you look into the circuit, you have to find out actually I and your V0, right. So this I you have to find out, and V0, and this is your I. This is your I is here. This is your I, right. And this voltage V0 actually here it is marked. This is your V0. This is across your 2 ohm resistor, right. And this is the circuit is given. It is a series parallel circuit, and this is a current source. This is a dependent current source, and this current is 0.5 V0. So for your understanding, this current, say this is a current source. Say actually IC is equal to, if you want, you can write say IC is equal to 0.5 your V0. So just it is shown 0.5 V0, and you have to find out what is the I and what is the V0. This is a dependent current source, and you have to solve this circuit. Now how we will do it? There is a, this is a 12 ohm resistance here, and this is your this is 12 ohm resistance. There are 2 ohm, here it is 10 ohm, and here it is 6 ohm, right. And voltage source is 100 volt, and current source, one dependent current source is there. Current is equal to 0.5 V0, and this voltage actually is V0, that is across 2 ohm resistor. And there are two loops. This is loop 1, clockwise direction we have taken, and this is another loop 2, right. So in this case, what you have to do is that you have to just hold on. You have to solve this one, right. So first what you do, apply KCL at node 1. Suppose if you apply KCL here, that is at node 1, this is your node 1, right. So here the incoming current is I1, this current is I, and at node 1 two are outgoing current, one is I1, another is I2. This is your node 1, right. So I is equal to I1 plus I2. So after KCL at node 1, if you apply, that I is equal to I1 plus I2. This is equation 1. This is equation 1. Now similarly you go to the circuit. This is your node 2. So and here just for your understanding, so this is you said this current, we said no, your what you call IC. So this is a dependent source current. So I actually current is 0.5 V0, 0.5 V0. So here if you apply KCL at node 2, so basically two currents are incoming current, that is your I1 plus this IC, right, is equal to the outgoing current is equal to I3, right. That means this is your I1, and this is IC is actually 0.5 V0 is equal to your I3, right. So if you apply your KCL at node 2, right. So let me make it this thing. So if you see here, that same thing we are writing, that I3 is equal to I1 plus 0.5 V0, right. So this is equation 2. Now we apply KVL in loop 1. So this is your loop 1, right. You are moving your what you call clockwise. So first you are encountering the minus sign of this 100 voltage source, 100 volt voltage source. So it will be minus 100, then plus your this current is this 12 ohm resistance, that current is flowing through this 12 ohm resistance I. So plus 12 I, right. And here also this your what you call this branch, right, that I2 is entering into this. So basically we can write either 2 into I2 or plus V0. So in this case what we have done it, that your in the loop 1 that minus 100 plus 12i plus your V0 is equal to 0, right. Actually V0 is equal to, if you look into the circuit, V0 is equal to, that from Ohm's law, 2 into I2, current entering the positive terminal. So V0 is equal to 2 into I2. So this is your what you call that in loop 1, that is your KVL in loop 1, right. This is loop 1. Now by Ohm's law also V0 is equal to 2 I2. Now apply KVL in loop 2. So here when we are applying KVL in the loop 2, you are moving in the clockwise direction. So it is encountering first is minus sign of this V0, that plus minus, that V0 is marked. So and voltage across 2 ohm resistance is V0. So it is encountering minus sign first. So it will be minus V0 plus that it will be 10 into I1, right. Then plus your it will be 6 into I3, because current through this branch is I3 is equal to 0. So, if you come to this, that this is minus V 0 plus 10 into I 1 plus 6 I 3 is equal to 0. So, this is equation 5, right. Now, from equation 4, that is from this equation, that is your V 0 is equal to 2 I 2, from this equation, right, that you substitute this in equation 3 and equation 5. That means, here in the equation 3 V 0 is equal to, you substitute your what you call, you substitute here V 0 is equal to 2 I 2. Similarly, here also in equation 5 you substitute V 0 is equal to 2 I 2, right. If you do so, you will get that 12 I plus 2 I 2 is equal to 100. This is your equation 6, and another one you will get minus 2 I 2 plus 10 I 1 plus 6 I 3 is equal to 0. This is equation 7. Now, we know that V 0 is equal to 2 I 2, right. So, V 0 is equal to 2 I 2, substitute in equation 2, that is your, this is your equation 2, right, this is your equation 2. So, this equation you substitute V 0 is equal to 2 I 2, this equation you substitute, right. If you do so, you will get your I 3 is equal to I 1 plus 0.5 V 0 and V 0 is equal to 2 I 2. So, it will finally become I 3 is equal to I 1 plus I 2, this is equation 8. Now, from equation 1 and 8, just you will get I 3 is equal to I, because I 1 plus I 2 is equal to, actually I we have seen before, just check equation 1. So, I 1 plus I 2 is equal to I, therefore, I 3 is equal to I, this is also I have marked as equation 9. So, from equation 7, 1 and 9 we get. So, what you do, you substitute all these things, this is very simple thing, I am not repeating this, just from equation 7, 1 and 9 you will get, just substitute all these things, you will get all minus 2 I 2 plus 10 into I minus I 2 plus 6 I is equal to 0, right. Or upon simplification, right, upon simplification you will get that 2 I 2 is equal to actually 8 upon 3 I, right, 16 I is equal to 12 I 2. So, 2 I 2 is equal to 8 upon 3 I. So, actually V 0 is equal to 2 I 2, that is why I did not write I 2 is equal to 4 by 3 I, just 2 I 2 is equal to I 3 I, this is equation 10. Now, solving equation 6 and 10 we get. So, if you just 2 I 2 is equal to 8 by 3 I. So, just solve equation 6 and equation 10, you just please do it, right, it is simple thing. So, just solving two linear equations, you will get I is equal to 75 by 11 ampere and I 2 you will get 10 upon 100 upon 11 ampere, and V 0 is equal to, you know, 2 I 2. So, 2 actually and 2 I 2. So, 2 into your what you call, and I 2 have got 100 by 11. So, it is 200 by 11 volt is equal to approximately 18.18 volt. So, this is your I, that means this is your I 75 by 11 ampere and V 0 is equal to approximately 18.18 volt. This is the answer, right. Next, take another example. You should be familiar with all sort of numericals. The second one is that, another one is that determine the currents and voltage in the circuit shown in figure, this your 2.25, right. So, it is your, here no question of any your dependent source, two independent voltage sources are there, one is 5 volt, one is minus 3 volt, right, and two loops are there, they are taken in clockwise direction, and across 2 ohm resistance voltage is V 1, across 4 ohm it is V 3, across 8 ohm it is V 2, and you have to your what you call, you have to find out the current and voltages in the circuit. That means, you have to find out your I 1, this current through this branch is I 1, this is here it is I 2, and here it is your I 3, right, and you have to find out also V 1, V 3 and V 2. From the circuit you can easily make out V 1 is equal to 2 I 1, V 3 is equal to 4 I 3 and V 2 is equal to 8 I 2, because everywhere current is entering into the your positive polarity of the resistance. So, sign is plus from the Ohm's law, that we have discussed before, right, and two voltage sources are there, it is 5 volt plus minus and a 3 volt, it are also minus plus, this way it has been marked. Now, what you do, you have to apply KCL and KVL, right. So, first you apply KCL at node A. So, this is my node A, this is my node A, right. So, I am not marking again by color A or ink, but this is your node A from the circuit. So, apply KCL here. If you apply KCL, incoming current at node A is I 1, right, and outgoing currents are I 2 and I 3. So, when you are applying KCL at node A, that I 1 is equal to I 2 plus I 3. So, I 1 is equal to I 2 plus I 3, this is equation 1. Now, you apply KVL in loop 1. If you apply KVL in loop 1, So, you are encountering first this minus terminal of the 5 volt DC source. So, it will be minus 5 plus, here it is, then you are moving like this encountering plus terminal again. So, minus 5, here it is plus V1, and here again also when you are moving clockwise encountering plus first. So, plus V2. So, minus 5 plus V1 plus V2 is equal to 0. So, that means this you are applying KVL in loop 1, it is minus 5 plus V1 plus V2 is equal to 0. This is loop 1. Now, and in loop 2, now here it is loop 2. Now, if you come to loop 2, you are moving your clockwise direction you are moving. So, first I am taking this one minus V2, this is minus V2, then plus V3, and then minus 3 is equal to 0, because it is encountering minus terminal plus your minus polarity first, because moving clockwise, then plus polarity first, then again minus polarity first. That means minus V2 plus V3 minus 3 is equal to 0, that is in loop 2. So, it is minus V2 plus V3 minus 3 is equal to 0, this is equation 3, right. Now, by Ohm's law I told you at the beginning that V1 will be from V1 is equal to 2 I1, because everywhere you will see currents are entering into the positive polarity. So, V1 is equal to 2 I1, V2 is equal to 8 I2 and V3 is equal to 4 I3. So, those things I am writing together, that V1 is equal to 2 I1, V2 is equal to 8 I2 and V3 is equal to 4 I3. All these thing combination is equation say 4, right. Now, substitute you V1 is equal to 2 I1, V2 is equal to 8 I2 in equation 2, and you will get, if you substitute in equation 2, that means this equation if you substitute in equation 2, right, you will get 2 I1 plus 8 I2 is equal to 5. This is equation 5. So, just little bit you simplify, right. So, every step if you write, it will take it will take consume lot of time, right. So, similarly, you substitute V2 is equal to 8 I2 and V3 is equal to 4 I3 in equation 3. That means, this equation you substitute V2 value and V3 value, this equation 3 you substitute. If you substitute, you will get your minus 8 I2 plus 4 I3 minus 3 is equal to 0, or other way I am writing 4 I3 minus 8 I2 is equal to 3. This is equation your 6, right. So, you solve from equation 5 and 1 we will get. So, equation 5 and equation 1. Equation 1 is equal, in equation 1 if you look at the equation 5, right, equation 5 I1, and in the equation 1 I1 is equal to your I2 plus I3. So, from KCL, that is your that is I1 is equal to I2 plus I3, that is equation. I will substitute there in this equation, right. So, in equation 5 we substitute that I1 is equal to I2 plus I3. So, it was 2 I1 plus 8 I2 is equal to 5, but here we are putting I1 is equal to I2 plus I3. So, 2 into I2 plus I3 plus 8 I2 is equal to 5, or 10 I2 plus, after simplification, 10 I2, because 2 I2 plus 8 I2, 10 I2 plus 2 I3 is equal to 5. This is equation 7, right. Similarly, from equation 6 and 7 you get the 10, that 6 and 7, just little bit you substitute and do it. 10 minus 20 I2 minus 8 I2 is equal to 3, right. So, if you go to the equation 6, this equation it is 4 I3 minus 8 I2 is equal to 3. So, just you put mathematical just substitution one after another. So, if you from equation 6 and 7, if you solve it, it will be 10 minus 20 I2 minus 8 I2 is equal to 3. Upon solving, I2 is equal to 1 upon 4 ampere, right. And substituting I2 is equal to 1 upon 4 in equation 7, you put I2 is equal to 1 upon 4, you will get 10 into 1 upon 4 plus 2 I3 is equal to 5. After solving, I3 is equal to 1.25 ampere, and we know from the equation 1 I1 is equal to I2 plus I3. So, 1 upon 4 plus 1.25, that is equal to 1.5 ampere, right. Therefore, V1 is equal to 2 I1, that is 2 into 1.5 is equal to 3 volt, right. V2 is equal to, already we have seen 8 I2, 8 into 1 upon 4, 2 volt, and V3 is equal to 4 I3. So, your 4 into 1.25. So, that is your 5 volt. So, V1, V2, V3 we got, and similarly we got I1, I2 and I3. So, you know now how to solve this one, right. So, these are the your what you call, these are the different techniques. Later we will find out some more different techniques to find out the solution of this. So, dependent source, independent source. So, things are quite comfortable and will be easier for you, right. Next is that your series resistors and voltage division. First we will consider the combination of series resistors, and then we will see the parallel one, right. So, series resistors and your voltage division. So, basically it is called series resistor, and this kind of circuit we call that voltage divider, right. How will come later. So, in circuit analysis actually then we have to need to combine the resistor either in series or parallel occurs frequently, right. So, we have to simplify the circuit, that is why we have to go all this simple analysis. So, in this section we will discuss that series connection of the resistor. So, now you consider this circuit, right. You consider this circuit a simple circuit, right. There are two resistors R1 and R2, they are connected in series, right. Voltage across them is V1 and V2 and their polarity are marked, right, and current through this circuit is I, and this is the terminal A and B, these two terminals are given, and across this terminal it is connected in series and one voltage source is there V and polarity is marked plus and minus, right. So, it is a single loop circuit with two resistors are in series and one voltage source is there, right. So, in this case we also apply same thing, that KVL one. So, by first if you first apply Ohm's law, from Ohm's law V1 is equal to I into R1 and V2 is equal to I into R2. So, that means your V1 is equal to I into R1 and V2 is equal to I into R2. Now, you apply KVL. KVL you go for your what you call that your clockwise you go, this is your you go clockwise, right. So, in this case it will encounter minus terminal first. So, it will be minus V, then you are moving clockwise. So, it will encounter plus terminal here for R1 and plus terminal here for R2. So, minus V plus V1 plus V2 is equal to 0. So, let me clean it, right. So, just hold on. So, in this case it is minus V plus V1 plus V2 is equal, or V is equal to V1 plus V2. So, V1 is equal to your here it is V1 is equal to, here it is IR1, right, and here it is your IR2, that is equation 20. So, here you substitute, then you will get V is equal to your V, it is IR1 plus IR2. So, ultimately it is V is equal to I into R1 plus R2, that is equation say 22, right. 2.22 because it is a chapter 2, that is why 2.22, but I will make 21, 22 like that, understandable to you, right. Therefore, I is equal to V upon R1 plus R2, right. So, that means equation 222 it can be written as that V is equal to I into Req, that is equivalent resistance. Req is equal to your R1 plus R2, right. So, implying that the resistors can be replaced by an equivalent resistor Req. So, that is Req is equal to your R1 plus R2, this is equation 25. So, equivalent circuit of figure 2.2 that is your figure 26, this for this its equivalent circuit will be now this one, right. So, this is your equivalent circuit, that means your voltage source will be there as it is, and Req is nothing but your R1 plus R2, and voltage across this is also V, because we have seen that V1 plus V2 is equal to V, because here it is your V1 plus V2 from equation 21, V1 plus V2 is equal to actually V, right. That is your source voltage. So, that is why here also it is written that your V1 plus, that is V is equal to V1 plus V2, that is total voltage. So, it is V and current flowing through this is I, right. So, this is the equivalent circuit. Now, to determine the voltage across each resistor, let us we substitute equation 23 into equation 20 and we will get. So, V1 is equal to then will become R1 divided by your R1 plus R2. It is very simple, just hold on. It is very simple that your V1 is equal to R1 into I, right, and from this your what, just hold on, let me clean it. Here from here, just hold on. From here your I is equal to your V upon Req, right. That means your I is equal to Req is equal to your R1 plus R2, right. That is your Req is equal to your R1 plus R2, and if you go to that your what you call that V1 is equal to your I into R1, right, because from the first circuit we have seen, that means your this one is equal to actually V divided by R1 plus R2 into your R1, that is your V1. If you first let me clean it, then I will go. All right. So, if you come to this circuit, V1 is equal to I into R1 and I is equal to V upon R1 plus R2. So, basically it is R1 into V upon R1 plus R2. So, that what we are doing here, right. So, what we are doing here, that V1 is equal to R1 by R1 plus R2 into V, right. Similarly, V2 is equal to your I into R2, and just now we have seen I is equal to V upon R1 plus R2. So, V2 is equal to R2 into V upon R1 plus R2. These two are equation 26. So, this is actually your what you call, if you or we can write that R1 plus R2 is equal to actually Req, because earlier that is Req. So, this equation V1 we can write R1 upon Req into V, and V2 is equal to R2 upon Req into V. So, these two equations we are writing as a complete equation. So, it is 27, right. Now, if you have n resistors are in series, then Req will be R1 plus R2 plus Rn. So, sigma k is equal to 1 to n into R 1 into n Rk, right. So, if you have n number of your resistors are in series, right. So, therefore, this circuit of 226 is called a voltage divider, right, because across R1 you will get V1, across R2 you will get V2 and so on, and across Rn the nth resistor you will get Vn. So, V should be equal to V1 plus V2 plus dot plus Vn, right, that you will get it. So, that is why it is called your voltage divider. In general, if a divider has n resistor in series with the source voltage V, the nth resistor will have a voltage drop of this thing, right. I mean, if you have Vn, then suppose your nth resistor is Rn, right, and if you have n number of resistor Rn, so it will be your Vn should be equal to Rn upon R1 plus R2 plus Rn your up to Rn into V, because the current actually I for if you have n, just a minute for you, I will make it for you, right. Suppose you have a circuit like this, suppose I am making it for here, suppose this is your voltage source. So, this is your V. Suppose you have a resistance R1, you have a resistance R2, and suppose you have a resistance your Rn, right. This is your R1, this is your R2, and up to say this is your Rn, right, and circuit is closed, and suppose current is flowing through this is I, right. So, your Req, that is your I is equal to, writing here, say I is equal to, it should be V upon your R1, whatever equation here I am writing R2, right, plus up to Rn, right, up to Rn. So, this is I. So, across your what you call voltage across this your this is Rn your nth your element, right, or nth resistor. Suppose this is your Rn, right. So, this is actually here it is you have n resistor and nth resistor. So, here what I can do is that you have taken nth capital. So, better you make it to capital, that will be better, right, make it Rn capital. So, this is Rn capital, suppose this is your plus terminal, this is minus terminal, right. Therefore, your and voltage across this, hopefully it is understandable to say Vn. So, Vn is equal to your I into your Rn, right, and Rn and I is equal to your writing here I is equal to your this one, just we got no V upon R1 plus R2 plus up to Rn, right, this one into your capital Rn, that whatever into V, Rn by this thing V upon R1 into capital Rn. So, here Rn I have written first. So, it is V upon this thing. So, this equation you further write that your what you call that Vn is equal to this Rn is I am writing here Rn. So, I am making Rn upon R1 plus R2 up to Rn into V. So, this way. So, hopefully I mean here little bit becoming clumsy, but hopefully it is understandable to you. So, let me clean it, right. So, this is for series resistor. Now, we come to the parallel resistor and the current division, that was series resistor and voltage division, and for in parallel resistor it will be parallel resistors and current division, right. Now, consider this circuit of figure your 28, right, where two resistors are connected in parallel and hence they have the same voltage across them. So, this is a simple circuit because this is a wire. So, these two are combined because it will be a single node because nothing is there in between these 2 points. Similarly, here also nothing is there in between these 2 points, here also nothing is there. So, if I further simplify for you, right, if I make it like this circuit, because here nothing is there, it is a wire, it is a wire and it is a wire. So, if you make like this, circuit will be like this, it will be a single node, right, it will be like this. This is R1, right, also it is your R2 connected like this and nothing is there, and this is your voltage source V. The circuit will look like this, right. This is your node 1, this is your node 1 and this is your node 2, right, and current flowing through this is I1, that means current through this is your I1 and current through this is your I2 and this is the current, that is your I, that is whatever this circuit is equivalent to this one, right, because it is all this is actually common point. That means your I is equal to basically I1 plus I2. If you write KCL at this node, that means this point, this is node 1 together because it is wire. So, at this node if you write, so this incoming current at node 1 I and 2 outgoing current I1 plus I2, that means your I is equal to your I1 plus I2, right. So, things are understandable, simple thing, understandable, right. So, let me clean it. So, now from Ohm's law you will get same thing, that V, or what you call V is equal to your this is a parallel circuit. So, voltage across this, just now I show this, that voltage across this, it will be your V is equal to, because same voltage will be impressed across this, just now I draw the equivalent circuit. So, V will be equal to I1 R1, similarly is equal to I2 R2 because there is no resistor, no other your electrical element is here and here. So, this voltage V will be impressed across these 2 nodes, right. So, it is a parallel circuit. So, V will be equal to I1 R1 is equal to V will also is equal to your I2 R2, right, understandable. I mean, there should not be any confusion. Okay, for you let me make it once again. Suppose this is same thing I am drawing. Suppose this is your resistance, another one, and this is one, this is your node 1, just now we draw, this is node 2 and this is the voltage source, right. I am making it here, this is the voltage source plus minus, right, and connected here, this is your R1, this is your R2, current through R2 is I2, current through R1 is here I1 and this is your I and this voltage is V. So, voltage across 1 and 2 is V actually. So, V will be equal to I1 R1 and similarly V will be your across R2 will be, this is R2 into I2. So, let me clean it, right. So, that means from Ohm's law, so V is equal to I1 R1 is equal to I2 R2 we can write. Now, therefore, from this equation we can write I1 is equal to V upon R1 and here also we can write I2 is equal to V upon R2, right. So, and apply KCL at node 1, I have told you that if you apply at node 1 I is equal to I1 plus I2. So, it will be your what you call I1 plus I2. Now, I1 is equal to V upon R1, I2 is equal to V upon R2. So, you substitute here I1 plus I2. So, I will be V upon R1 plus V upon R2 is equal to V 1 upon R1 plus 1 upon R2, right, or I is equal to, we can write V upon Req, right. That means, what we did that this one, so we are writing V upon Rq, that means what we are doing is we are actually writing 1 upon Req is equal to 1 upon R1 plus 1 upon R2, right. So, because I is equal to, you have to make V upon Req, that is the current I. So, 1 upon Req actually 1 upon R1 plus 1 upon R2, that what we are actually you are writing, right. So, that means that it is the equivalent resistance. So, 1 upon Req we have 1 upon R1 plus 1 upon R2. So, Req actually is the equivalent resistance. So, otherwise Req is equal to R1 R2 upon R1 plus R2, then product of two resistance divided by the sum of the two resistance, right. So, Req is equal to R1 R2 upon R1 plus R2, this is equation 35, right. So, in general if you have n resistors are in parallel, then 1 upon Req is equal to 1 upon R1 plus 1 upon R2 up to 1 plus 1 upon Rn, right. So, you take summation of reciprocal of that, and then you take the your what you call that further your inverse of that, right. So, 1 upon Req is equal to 1 upon R1 plus 1 upon R2 up to plus 1 upon Rn. So, that Req is the equivalent resistance. So, figure 2.29 shows the equivalent circuit, that is your Req. Req means this is the equivalent circuit, right, which basically just hold on, basically this is your Req is equal to R1 R2 by R whatever we have written R1 plus R2, right. So, and this is the node 1, this is node 2. So, across Req voltage impressed is your V, same voltage V will be impressed. So, V is equal to actually I into Req, right. So, if you write V is equal to I into Req, right. So, things are understandable, right. So, just hold on. So, that is what I told, V is equal to I into Req. Now, Req is equal to, you know, that is I, Req is equal to R1 R2 upon R1 plus R2. Because substitute Req is equal to here, that is equation 38. Now, substitute equation 38 into equation your 31, that you will get. So, you will get I1 is equal to your what you call R2 upon your R1 plus R2 into I, because you know this one, if you go to equation 31, that is your this equation, right, that is I1 is equal to V upon R1 and I2 is equal to V upon R2, right. So, when you are coming here, that I1 is equal to your V upon here, I1 is equal to V upon your what you call V upon R1, right. So, and your that means V upon R1, if you take this one, you will get I into R2 upon R1 plus R2. That means your if you just hold on, from this equation only you will get V is equal to I into R1 plus R2 upon R1 plus R2. So, from this equation you will get no that is V upon your R1, right, that is nothing but your I1, right. From this equation if you write, it is basically look R2 upon R1 plus R2 into your I. Same thing is coming here, I1 is equal to R2 upon R1 plus R2 into I. From this equation only, just divide this equation by R1. So, V upon R1 is equal to R2 upon R1 plus R2 into I. Similarly, for I2 is equal to your V upon R2, I2 is equal to V upon R2. So, this equation you divide by R2. So, basically your I2 is equal to V upon R2. So, divide this equation by R2, you will get R1 upon R1 plus R2 into I, you will get R1 upon R1 plus R2 into I. So, right, so directly you are getting that I1 and I2. So, current division. Now, if you look into that, just hold on, let me clean it. So, just if you see that equation 39, that is I1 is equal to R2 upon R1 plus R2I, or I2 is equal to R1 upon R1 plus, that indicates that a total current I is shared by the resistor in the inverse proportion to the resistances, right. So, circuit shown in figure 28 is called the current divider. So, if we go to equation circuit figure 28, this circuit actually is called that current divider, right. So, so it indicates that equation 31 indicates that the larger current flows to the smaller resistance is understandable to you, right. So, as extreme case, say R2 is equal to 0, short circuit, as shown in figure 30, entire current I bypass R1. If it is a short circuit, then R2 is equal to your basically 0, right. That means equivalent resistance, say Req is equal to R1 into R2 by R1 plus R2. So, Req will become 0. So, it is a pure short circuit. If you make either of these, either this one R2 is equal to 0 or R1 is, either of these you make short circuit, and both 0 also short circuit, right. So, it is a pure short circuit. So, thank you very much, we will be back again.